So welcome everyone. This is the 41st Quant University weekly lecture series. So we started this tradition of a weekly Quant University lecture when COVID hit last year. And as you know, it's been a long time since then. And I'm pretty sure everybody is ready to get back to the new normal, if you will, and getting back to the offices. I see the traffic lines getting longer everywhere. It used to take me 20 minutes to get into Boston, into the city of Boston just a few months ago, and now it's back to 40, 45 minutes. So I guess life is slowly returning back to normal, and we are going to get used to getting back into the traffic delays and waiting in the traffic and trying to multitask as much as possible and go for the dreaded lines for the restaurants and the cafeterias and all the other things. But I'm hopeful that the summer is going to be good for you all, and I hope you are able to get a chance to relax. So today we are very excited to have Siddha Ganju from NVIDIA to join us as a guest speaker. I came to know about Siddha's work through her really popular and pragmatic book, Practical Deep Learning for Cloud, Mobile, on the Edge. And I'm pretty sure Siddha is going to talk a little more about her book and what inspired her to write this book. So Siddha, as many of you know, has been working at NVIDIA as a self-driving architect. And I'm going to just read her bio. So previously at Deep Vision, she developed deep learning models for resource-constrained edge devices. A graduate from Carnegie Mellon University, her prior work ranges from visual question answering to generative adversarial networks to gathering insights from CERN's petabyte scale data, and has been published at top-tier conferences including CVPR and myriad. So as an AI domain expert, she has also been guiding teams at NASA as well as featured as a jury member in several international technical competitions. And she's also a 30 under 30 from Perth. So welcome, Siddha.
Thank you, Sri. Thank you very much for having me.
Yeah, you're welcome. And we're very excited to hear you. So before we get started, I'm just going to make a couple of quick introductory remarks and housekeeping announcements. So just a second. So I hope you're all able to see my screen. So all the slides and the presentations of the prior sessions are available on Q Academy for people who are interested in reviewing the lectures. So I'm just going to tell a couple of things before we get started. Okay, so this should have. So as you all know, we are Quant University. We're based out of Boston. We started doing these sessions last year, and we've been primarily focused on the intersection of data science, machine learning, and finance. And in addition to that, we have been running the Quant University Summer School 2021. And we've been doing a couple of different programs, one in the area of machine learning and finance. And we have two courses, which is going to get started today, just enough Python for data science, and another course on machine learning and AI for financial professionals. And we also have a couple of courses in the AI and risk management series, one on risk and ML models, stress scenario testing and evaluation. That's a 6-week course, which is starting again in July for the second cohort in the summer. One on algorithmic auditing for machine learning and AI models. And the third course is a model risk management for machine learning models. So if you're interested in any of these courses, just go to the URL or just scan the QR code, and you should be able to get more information and download brochures regarding the courses. And as I mentioned, today's lecture is going to be hosted by Siddha. And then next week, we have another lecture from NVIDIA. As many of you know, Quant University is an NVIDIA inception company, so we've been doing some work with them. And we have Jochen Papenbrock from NVIDIA, who's going to be talking about responsible AI. And he's been doing some interesting work on synthetic data generation, on scaling up on GPUs. So it'll be a very interesting session. And then the week after that, we are doing a session on how do you audit deep learning models. So I'm going to be presenting some of the research we have been doing here at Quant University on the theme of algorithmic auditing, primarily when you are working with really large scale deep learning models. And again, as I mentioned, all the slides and the demos will be available on Q Academy. So those were the announcements I had. So Siddha, I'm going to hand over the stage to you. So welcome again, and please take it away.
Thank you. I will start sharing my screen. So it still says that the recording is paused.
It's being streamed online,
okay.
so that's fine.
Got it.
So
that makes sense. Can you see the slideshow view?
Yeah.
All right. Awesome. So thank you, everybody, for being here. And thank you, Shri, for having me. Today, I'd like to talk about how do we improve performance in a deep learning system. And we're really going to be focusing on the end-to-end pipeline. So starting right from the data, going all the way to training and, of course, deployment. But before I begin, I want to tell a little bit of a story of how these 30 golden rules came out to be. Now, I'm sure with the work from home, a lot of us are spending a lot of time on the internet, sometimes even more than we expect. But there's a thing going on the internet which says that if you want to be really good at something, you have to spend 10,000 hours on it, right? Now, numerically speaking, that 10,000 hours is a little more than a year, which really means that if you want to be really good at something, you've got to dedicate an entire year just to understand and figure that out. But I mean, in our busy lives, we don't really have a year to dedicate to absolutely everything that we may want to learn. And that's where we have best practices or golden rules or learning from other people's experiences. And that's exactly what my co-authors Anirudh, Meher, and I have done. We have been working in the industry for a few years, and we've learned a lot of things along the way. These are things that we learned not just by failing, relearning, and learning again, but also things that we've learned from people who have come before us. And so all of this golden knowledge is something that we've condensed into these 30 golden rules. And these rules are really just a small part of the knowledge that we've been able to understand and learn over the past almost 25 years worth of cumulative experience. And so all of that knowledge is also in the book, the Practical Deep Learning book that Shri mentioned, and I'll just be going over a little bit of it today. Another little story that I do want to share is in our last chapter about how can we create an autonomous vehicle in the virtual environment of AWS Deep Racer. As a slight nudge to our readers, we said, you know, you've created this really amazing car in the virtual environment of AWS Deep Racer, and the next step is to take it into the real world with the Robo-Race Competition. And amazingly enough, a few months later, a team from Carnegie Mellon University actually joined this competition. They landed on the podium, and that's not it. They actually worked to release a framework that allows people to train RL-based autonomous vehicles, which is a pretty interesting piece of work coming from, you know, a completely student-led team. So I encourage everybody to go check that out as well. Okay, so let me start off by making sure that all of us are on the same page and talking about training. So we can almost always assume that transfer learning encompasses almost 95% of all AI training. And what does transfer learning really mean? Well, transfer learning is, you know, the kind of knowledge transfer you do when you have some background knowledge. So let's say I want to learn the musical instrument, the melodica, and if I want to learn this from scratch, it will take me, give or take, 3 months. But if I already know how to play the piano, then all I need to do is fine tune my skills from the piano to the melodica, which in this case may mean that I need to learn the breathing pattern as I press the keys, because I'll probably have the musical theory knowledge and knowledge of the keys from my piano playing skills. So in a sense, what transfer learning is trying to do is it's trying to snip away the task X specific layers and replace them with a task Y, which is a new task. So replacing piano with melodica. And this, in a sense, is what transfer learning does. Now, painfully in life, I think we sometimes may have experienced that what we really want is not always what you can afford. And so what are the techniques to make the car on the right, the green car, really boost up its speed and performance to make it as close as possible to the car on the left, the maroon car? So these are the techniques that we will talk about today. And when we talk about what exactly is it that we want to optimize or look for, we see that the culprit for the slowness is usually starvation. Now, this could be CPU starvation or GPU starvation, or really any kind of hardware starvation. And what starvation really means is that there are some cycles in the CPU, GPU, or TPU that are idle. Now, looking at the usual process workflow, we see, the CPU is preparing a batch of data. Meanwhile, the GPU or TPU may be idle. When the batch is prepared, it's sent over to the GPU or TPU. They start training or doing whatever processing. And during this time, the CPU is idle. And so this idle cycle keeps on continuing. And these are the exact seeds of improvement for us, because the CPU, the GPU, the TPU are being starved. So we know what to optimize, which is the starved or the idle cycles for any hardware, right? We want to optimize that. And how will we know what it is that we have optimized, or how much have we optimized by? So for that, we call for some profilers. Now, the profilers are really interesting because they provide almost a visual understanding of what's going on the CPU, the GPU, or the TPU. So here, as an example, we have the Tensorflow Profiler, which appears in TensorBoard. And you can see from the 0 millisecond to the 120 millisecond mark, that's a totally empty timeline, which means that the GPU isn't really doing anything. And that's exactly what we want to fill up with our data improvement, data loading, reading, or training strategies. Setting up the TensorFlow Profiler is also relatively easy. It does require a little bit of setup, but overall, I think it's pretty doable. But at the same time, there may be some use cases where you may not be looking for something as advanced as a TensorFlow Profiler. So in those cases, we have something very simple known as NVIDIA SMI, or NVIDIA System Management Interface. And the one number to really look for here is the GPU utilization, along with the processes that are running on the GPU. So this really tells you how much of the GPU are you using. And ideally, we want to go from this 51% number to a much higher, ideally in the late 90s region. And you can run the NVIDIA SMI command again repeatedly by appending it to the watch command, which means that every half a second, the NVIDIA SMI command will be repeated. So it'll be refreshed on the terminal, and you can see the latest statistics every half a second. All right, so we know what to optimize, which is the GPU starvation, and we have a metric or a measure on knowing what the improvement has been through the profilers. So now we'll break it down into data preparation, reading augmentation, and then go into training and inference and go through some methods of optimizing each of these processes. So starting off with data preparation. Now, there are a few anti-patterns when it comes to data sets, right? One of the common anti-pattern is that data sets are usually stored as several tiny files. But at the same time, they're also usually stored in, really big, gigantic, multi-gigabyte file. And both of these offer a lot of overhead while seeking the files, right? And you can imagine if you are reading over a network, that adds even more latency to the system. So the solution here is to combine several of these 1,000 files into a handful of large files. But the important point, to keep in mind, is the size of that file, right? And what format do you want to store it in? So the format should ideally be in the protobuf or the protocol buffer format, which is used to store models at scale. And as you can imagine, models can be pretty big. So it is a very efficient format for storing not just models, but also the data. And the sweet spot size for these combined files should be around 100 megabytes. And this 100 megabytes is good enough even if you're reading data over a network. It doesn't really add that much latency to the overall system. Then another idea is to reduce the size of the input data. Now, when we write a pipeline, we usually read a bunch of images, we do some processing on it, we may resize, we may do some augmentation, we then train, and then we kind of repeat this pipeline over and over again. But if we know what pre-processing we want to do, if we know, that we have to do resizing, or if we know that we have to do these specific kinds of augmentations, then we can save that pre-processed data as a TF record dataset. And so it makes the process easier because it removes the time taken to pre-process away from the overall pipeline and just makes the process much more quicker and easier. And at the same time, we see a lot of pre-processed data sets being available out both in the TensorFlow environment as well as in the PyTorch environment. So why not use those pre-processed data sets? And importing these data sets is also relatively easy. You just really import the name of the data set, and these are updated every now and then. For example, we have the Chexpert dataset, which is relevant for COVID-19 research. So as you can see, the datasets are updated every now and then. And it's also really easy to process these datasets. For example, you can easily split it into a well-defined training, validation, test set. You can define what batch size you want. You can shuffle the data set. So the processing on top of TensorFlow datasets is relatively easy. And a pro tip here is if you've been working on a really niche data set, a good idea is to actually generate a TensorFlow record dataset out of it, but also to release that dataset so that it's easier for others to build on your work. And this really promotes open science and research building off of your work. All right, moving on to the data reading portion. So data reading means that we want to optimize the process of reading all these files. Now, in order to do that, let's build a very basic pipeline that just reads a bunch of TF record data through the TFDS functions. And what we're trying to do here is, we're trying to shuffle the data. We are linking the data point with its label, resizing it, and adding a batch. So processing the size of the batch as well. Now, in this reading pipeline, we will also add a bunch of augmentations and go through some steps one by one, which ultimately will make the reading almost 10x faster. So let's see how to do that. Now, one really common idea is to prefetch the data. And prefetching basically means that you want to get rid of the circular dependency that the CPU is waiting for the GPU is waiting for the CPU, right? So we want to avoid the circular dependency. And in a sense, we want to make sure that there is a buffer of data that's always available for the GPU to consume, right? And how is it going to do that? It's going to do that by maintaining an asynchronous buffer that is always available for the GPU to tap into. And this is relatively easy to accomplish by appending the prefetch option onto the dataset. And you can also define the buffer size. Ideally, this buffer size should be equivalent to the size of the batch, so that the next, the complete next batch is ready for the GPU to consume. Next is to parallelize CPU processing. And usually this should be done in an equivalent number to the number of CPU cores. Otherwise, there may be too much context switching, and it will actually slow down the overall process. Now, of course, we want to use those cores for parallelizing IO and subsequent processing. And what we really notice here is similar to the traffic example that Shri mentioned. When we're in traffic, a single slow car can really hold up everybody else, right? And so similar to that, if there's a single slow file that is being really slow to read, it's going to hold up absolutely everything else. So we want to interleave here, which means that we want to parallelize the IO and their subsequent processing. And so again, this is doable with the interleave option. And again, we want to make it equivalent to the number of cores that are available. Now, enabling non-deterministic ordering. Now, when we look at most of the pipelines, we shuffle the data when we read it to make sure that there is no implicit ordering in the data that the training may pick up, right? Given that, we don't really need to read the data in order then, right? And so that's why enabling the non-deterministic ordering is really helpful, where if we don't need to read the data in order, then we can just read the data in whatever order it's written in on the disk. And so that is enabled by the experimental, setting the experimental deterministic to false. And this is one of the options that you have to enable from the TF data options. Another really good idea is to cache the data, right? Caching basically means that you have an easy access store where you can always take the data from, and you can always cache both in memory or on disk, depending on how big the amount of data is that you're looking to cache. But at the same time, you want to avoid repeatedly performing certain operations. Like if there are CPU-based operations, like a lot of augmentations or resizing, you want to avoid that. And so you want to cache the data that is processed. So cache data that is, let's say, resized or augmented onto your either memory or disk. And then turning on experimental optimizations. A lot of the frameworks that we use today, they are community-based. And so there are a lot of changes going on in it every now and then, which also means that there may be some optimizations available that are not really pushed to the downstream branches, but are upstream. And so in order to see those experimental optimizations, you can just set the different options to true and just see if you get a speed up from those experimental optimizations. Now, auto-tuning parameter values. This is one of, I believe, the most important questions that I've also dealt with. There are so many parameters to tune in while training a network, but what's the best value for the parameters, right? And on top of that, how do I make sure that these parameters are the best parameters for whatever hardware I have, right? Whatever hardware I'm training on. And so all you really have to do is forget about it and just use the experimental auto-tune features. And the good thing about auto-tune is it tunes all the parameters that you have. I mean, of course it does that, but it tunes it to the best options for your hardware type. So depending on, which GPU you have, there may be different memory, there may be different, different speed at which you can run everything, depending on what other things are running on your system as well. So auto-tuning the parameter values is a really good option to try out. And, combining all of these things into a single pipeline kind of gives us this end-to-end data reading pipeline. And, this is much faster than what we had before. And this is a really good basis to try out for experimentation at scale. And that brings us to data augmentation. So, augmentations are really diverse, and there are, I would say, are almost two things to keep in mind while looking at augmentations. One, that most of our frameworks, OpenCV, Pillow, Keras, because they're community-led, they initially started out with just doing augmentation and processing on CPU, which means that if you have access to a GPU, you're not really using that GPU. And so the idea here is to utilize a framework that allows you to use the GPU while performing those augmentations. So an example of this would be tf.image, and this seamlessly plugs into the TF data pipeline, so it makes it easier to consume this. Keep in mind that this is still, a work in progress, so you may not have a lot of the built-in or the really fleshed out augmentation functionality, but at the same time, it's being built. So there's a lot more coming. Now, if you're looking for a more generic, more framework agnostic solution, then we have NVIDIA DALI that actually is being used by all the industry benchmarks to break the industry benchmarks, for example, to train on ImageNet in less than 80 seconds, and they're just using the NVIDIA DALI pipelines. And NVIDIA DALI not just does the augmentation really well, but it does loading, encoding, decoding for not just images, but also videos really well. So NVIDIA DALI is a really good framework for testing out in your pipeline and seeing the amount of speed up that it can bring. All right, on to the more interesting, I would say the most interesting or the most time-consuming part, which is the training. So a really quick fix for training is to use automatic mixed precision. And because you're reducing the precision at which the compute is happening, you're really making the training a few times faster, usually 2 to 3 times faster. And it's really easy to do that. All you have to do is set a flag to 1 or true. Now, it is really important to understand that automatic mixed precision is, almost a magical tool, because if you were to do mixed precision manually, it's a little bit complicated because you have to have 2 copies of the model, right? One in a higher precision, one in a lower precision. And you have to maintain both the copies of the model so that you don't lose out the tiny improvements that are being made when you're doing the forward and the backward passes, right? Because let's say you have a ReLU operation and the change to the weights are, let's say, 10 raised to power minus 6. And if you're adding that really, really small number to something like a weight of 1, you will still be at a number that's still really, really close to 1. And so you want to make sure that all those tiny weight improvements are not being lost. And that's why we need to maintain both the higher precision model and the lower precision model. And that's exactly what the automatic mixed precision does for us in a much more simpler and easier to consume way. Another idea is obviously to use the larger batch size, or honestly, the largest batch size possible. So on some of the more recent GPUs, like the TX2Is, or the V100s, you can actually get a huge amount of RAM, around 11 GBs. And so if you were to train something like a mobile net on it, even with a really high batch size of around 500, 600, you would still get just around, let's say, 80% utilization, which means you can still boost up either your batch size or your image size, or even the network architecture in certain cases, to get to those 90, 95% utilization. And so in this case, we can definitely increase the batch size from 500, 600, maybe go to 800s. We can also go with a much bigger model, for example, replacing mobile net with a ResNet 50 architecture, and that will almost always boost our utilization of the GPU to 90, 98%. And that's exactly what we want to do. We want to make sure that our batch size is fully capable of utilizing all the GPU, obviously the number of GPUs that we have access to. Now, when it comes to understanding the batch size, it's always ideal to use multiples of 8. And the reason behind that is because as you go as you go higher or lower in terms of hardware, so you go from CPU, GPU, TPU, you see that the underlying arithmetic in it is always should always be divisible by 8. And so that's why using a batch size that is a multiple of 8 is really helpful in speeding up our operations. And so the best batch sizes, are usually, for some of the more recent architectures, GPU architectures, to use around 256. And for some of the TPUs, it really depends on the number and the type of TPU you have, but we've seen sizes from 128 all the way to 1024 for some of the more recent SimCLR type self-supervised networks. So it's a huge range of batch sizes that you can choose. All right, learning rate. Learning rate, I think, is one of the most I want to say non-hardy parameters, because if you don't fix it properly, then your training is just it may take too long to converge, it may never converge. So learning rate is really something that we want to think about before we set. But really understanding what the initial learning rate should be can become really complicated, especially if you're trying out a new task or it's a relatively new data set. And so we have this really cool library known as the Keras LR Finder library that finds the mathematical definition of learning rate, which is, the greatest the point of the greatest decrease in loss. And so it basically finds that point in the first few runs. It gives you that learning rate, and then you can use that learning rate for training at scale your network. And I think this is a really cool library to especially test out when you have something new to try out. Another thing to keep in mind is tf.function. Now, tf.function really came into the picture when TensorFlow moved from their graph-based execution to their eager execution in TensorFlow 2.0. And moving to the eager execution meant that there was a very, very small loss or an overhead, which came because you had to execute almost everything line by line. And so the idea here is, if you have these really small functions, you can add tf@tf.function to the top of the function to enable graph-based execution for that particular function. And so in our example here, we see that we're just applying a simple convolutional function over a piece of data, and we see that with tf.function, there's almost 10x speed up. So if you were to do the same things again and again, this 10x would add to a much, much bigger number depending on what the size of the image is or the size of the data is and how many times you're doing the simple convolution operation as an example. Now, another rule of thumb is to overtrain and then generalize. And this may seem counterintuitive at first because you're asking the system to overtrain, which we all know is not always a good idea. But the idea here in overtraining and generalization is that you want a pipeline to at least learn something, right? Just to show that the task is doable and there is some accuracy that we can later obtain in this problem. And so a quick example that I like to share here is, if I have to learn French, I have two options. I can either, open the dictionary, learn every word that there is in the dictionary, or I can pick the 50 most common words, learn them, pick another 50, and so on. And so what we're doing in the second option is really overtraining on these 50 words and then generalizing, adding another 50 to the batch, overtraining, and then so on. So this overtraining and generalization has been quite explored in several areas. For example, and then add 10 more classes to the mix and then 10 more and so on. So you're progressively increasing the samplings that are shown to the network. Same for augmentation. You can start off with one augmentation, then add another augmentation, and keep in mind that all of these steps, because we are performing them as individual steps, it makes the network easier to debug as well. And then we have progressive resizing. And again, as seen on the FastAI courses, where they actually take a much smaller image to start with, let's say a quarter width and a quarter height, or a half width and half height. And they experience much higher speed ups, but at the same time, they show that, okay, training on these kind of images is still possible, right? So when you're doing training on much smaller images, you at least can figure out what the network architecture should be, what kind of augmentations may be relevant. And once you're fixed on that, you can train at scale with a much larger resolution, and you can much more quickly get to the final neural network architecture. All right, so the next one, installing an optimized stack for the hardware. I honestly think this is the most important thing. And the reason is, when a framework releases their hosted binaries, the binaries are expected to run on a range of hardware. And so if you have a system, excuse me, and so if you have a system that is pretty recent in terms of the hardware, the hosted binaries are still meant to run on not just the most recent hardware from today, but also hardware that, let's say, came out 5 years ago. And so as an end user, you really want to make sure that the framework that you're using is optimized for the hardware that you have. So as an example, if you're using TensorFlow, you really want to build it from source, which would mean a basal build. So it really utilizes the instruction set available for your particular hardware, right? And obviously that is a very intensive process. So you can also use Anaconda, which kind of automatically does the processing for you. Or if you have containerized workflows, you could also use NVIDIA's NGC containers, which also do the trick and are much easier to use. All right. So the next one is to optimize the number of parallel CPU threads. And now we've talked over this when we were looking at data reading, but in terms of training, we still want to exploit this. And again, we want to set it equal to the number of threads that are available. And so we want to do this both in an inter-process way and an intra-process. So both on a per operation level as well. So we want to do both for parallelizing CPU threads. And then, of course, using better hardware, right? So if you look at some of the time progression, a few years ago, we had the V100 GPUs. And when we combined 16 of these V100 GPUs, which was known as the DGX2 machine, the combined set gave 2 petaflops. But some of the more recent hardware, the A100 that came out last year, this one chip gives 5 petaflops. So obviously better hardware, much improved performance. So use the better GPU. Now talking about multiple GPUs, you can always distribute training, and it's good to note what kind of training or distribution strategy to use depending on what kind of hardware availability you have, right? So if you have a single node, multi-GPU or multi-node, multi-GPU setting, you would want to distribute your training accordingly. Excuse me. Or you can always use Horovod, which was a framework released by Uber, to distribute the program on multiple nodes as well. Moving on to the industry benchmarks. So benchmarks are a really good way to see, what kind of hardware is good, what kind of architecture should I start from? And these are, so there are multiple kinds of benchmarks, but the most important ones usually show us the time and cost. So for example, here we see, all these teams are training ImageNet for just $7. And I believe this is for just 2 minutes. So this really shows you the amount of expertise in terms of distributing the code. And these are almost always associated with a research paper or some kind of a paper that talks about how they distributed the code and how they worked on it. So if you're trying out a new task, it's always good to examine the industry benchmark and see if there's something readily available that you can use to really get up and running quickly. MLPerf is also another really good industry benchmark, and it's more focused on the hardware. So the amount of accelerators that you're using and the amount of time that it's taking, of course, to train MichNet, as that's a standard industry standard. And fortunately today, we can even rent an entire supercomputer on the cloud with a lot of GPUs and cores. And so it's just a matter of what task is it that you would be interested in. Okay, so moving on to inference. So inference is really considered the opposite of training because, in training, we're looking for as big a model as possible, add as many parameters to it. And on the inference side, we want something that's really small. So I like to say, does your 500 megabyte model spark joy? If not, just, discard of it. And so there we have starting off with an efficient model. And these really fit into different kinds of tasks. So for example, if you're doing classification, you want to start off with, excuse me. So if you're doing classification, you want to start off with, the mobile net. Sorry about that.
Meanwhile, take a break, Siddha. If there are any questions, please use the chat window to type in. I know it's a lot of details, so if anybody has any questions, please feel free to put in the chat window so that Siddha can answer after the presentation.
Thank you, Sri.
Yeah.
So while the questions are coming in, I'll just finish off. I have just very little left. So again, for classification, using MobileNet or NASNet mobile, which is again really dependent on the hardware that you have. And then for detection, we have efficient detect. And for NLP, it's like almost every single day we have a new model with so many more million parameters coming up, or I should say billion parameters. But the idea is to use something that's really optimized. And so that's where we have the DistilBERT. And you can see here the number of parameters is actually pretty less, but the accuracy is something that we're not losing when we're comparing it to some of the more state-of-the-art networks like BERT. And inference is really where we see quantizing the model or reducing the number of bits that are being used for inference in the final model. Now, quantizing is something that's really dependent on the target hardware and the framework that you're using to deploy the models. So for example, here we see results of deploying a model on CoreML, which deploys to Apple devices. So an iPhone, an iPad, such. And we see that quantizing to 8-bit doesn't actually lose accuracy, but the size it's pretty small. And so choosing choosing whatever framework and using the quantization solutions available on those frameworks is always a good idea. And of course, pruning. So pruning makes sure that the model, it doesn't actually remove the weight. It removes the weights that are really close to 0, but it doesn't reduce the size because the weight connection is still there. And so what you really want to do with pruning is you want to make the model as compressible as possible. And this allows for really good transferability. For example, if you're updating the models and such. And pruning is, again, really easy with the pruning API that are available. For example, in Keras, all you have to do is just encapsulate the layer and it'll prune it. Another one is to use fused operations, which is to combine linear operations so that the result is still a linear operation. But because it's a pre-computed operation, you don't really use the time during inference to compute that. So that's a huge advantage. And especially when it comes to convolution layers, because they are pretty common, and can be fused. It really reduces the amount of time at inference. So GPU persistence is really the last golden rule. And the idea here is if you're loading some GPU drivers after a really long time, or if it's a cold machine, it's not a warm start, the driver will take some time to load. So you can avoid that by making sure that the driver is actually persistent for your user and the machine that you're using. And this really helps in really running even your first iteration really quickly. And so those were the 30 golden rules. If you want to access the slides, all you have to do is send a wget QuantUniversity presentation to practicaldlbook@gmail.com, and you will get access to the slides and a copy of these 30 golden rules. And I hope you can optimize your pipelines accordingly. Thank you. Happy to answer any questions.
So Siddha, could you just type in the wget QuantUniversity
Yes.
in the chat window?
Yep.
Okay, and we'll be sharing it on our portal also, the test rates. So thanks so much for presenting. I know it was a lot of information in a very short period of time. So I actually had a question about when you, obviously you have a lot of access to GPUs. So optimizing is probably not something you would start with, but you will have to design it so that you'll have to ensure aspects of it are optimized from a customer's perspective. Now, GANs, are there kinds of best practices for leveraging GPUs for GAN-based architectures? Are you looking at things which are what do you call architecture-specific design aspects, or would you look more from a framework perspective, like we are going to optimize this for TensorFlow or for PyTorch or this particular hardware architecture, etc.?
That's a really good point. I think at the end of the day, it really boils down to three main things. And all those three things are things I think that you've already mentioned. One would be the framework that you're using, because the framework really needs to interact with the underlying hardware and it needs to do it really well. The second would be the kind of task that you are working on. So if you're using GANs, if it's, what kind of operation are you trying to do with the GANs? And we've seen a lot of differences when it comes to, let's say, you're distributing training with detection or classification, right? It's much more easier to do it with classification because it's just a much more stable training strategies. And so understanding the task and its implications on, how can we distribute it really well? What kind of parameters are really good to starting off from? I think those really help. So we talked about the framework, the task, and third would be understanding the what kind of GPUs you have. Now, when we say what kind of GPU you have, it really means the amount of memory that is available on those GPUs that allow you to, train at a much faster rate. And making sure that you are taking advantage of everything, like all the memory that the GPU has to offer. And that part is kind of something that we went into in the data reading and the training portion. So really understanding, are we able to, go to that 90 to 95% utilization all the time? And so to measure all these three, again, we would need to profile it. And profiling is really good because it gives you an end-to-end picture, right? So when your data started reading, were you still seeing a high utilization when you were training? At the end of the first batch, did you see a valley in your profiler? And so all these things really tell you which exact position in your training or your end-to-end pipeline do you need to optimize. And I'll also say that, in the profilers, you also have an understanding of, which operation, for example, if it's a convolutional kernel, how much time is it taking? It'll also tell you that, let's say you had 20 convolutional kernel operations, and sometimes one particular operation takes much longer than the others. So you should be able to, like within the profiler itself, it tells you, okay, this was taking this long, which means that, there's something really wrong over here. So that's something that is an opportunity to fix things up. So I think focusing on all these three and using the profiler to really measure the improvements as you are improving your end-to-end pipeline would probably be how I would go about it.
Okay, cool. I think we're going to run out of time in a minute or two. So two questions. One, when you're thinking about optimizing for memory so that you can load your data sets, how do you kind of look at your system memory versus memory on the GPU? Do you match it? Like, I mean, hardware architecture-wise, do you typically say, okay, I'm going to be moving stuff to my GPU memory anyways, so I need to have a lot of memory on my GPU memory, or what kind of recommendations do you typically have?
Yeah. So in that, what I like to see is how much of the data and how much time is that data spending on the CPU, right? So if I'm, let's say, reading and doing augmentations on the CPU, which means that the data is going to spend a lot of the time on the CPU, so it's going to be CPU bound. If I can move that processing, for example, doing augmentations on GPU to the GPU, it means that I can actually use up all the memory that the GPU has to offer, which means that the processing will ultimately be much faster. So understanding if the processing is IO bound, CPU bound, and then, kind of mitigating those binding techniques by either moving to the GPU or figuring out, okay, if it's IO, then maybe we can parallelize IO and so on. So knowing what kind of the, I want to say pain point is, will really help in understanding what are the mitigating measures, because it may be different in each case.
Got it. Thank you. So last question. So are you guys allowed to mine crypto?
Sorry?
Are you allowed to mine crypto using GPU resources?
No.
Okay, so it's a bummer. We could have deployed all the GPU power for testing.
Well, but the good thing is that we're training at scale and utilizing everything, right? So I don't think there's anything left to run any other operation.
Okay, cool. Okay, cool. Thank you, Siddha. It was really enlightening. I'll definitely get a copy of the slides. And also, I highly recommend Siddha's book, Practical Deep Learning for Cloud, Mobile, and the Edge. And I hope to catch up again soon, and hopefully at our another technical discussion to understand more about how things are evolving, both from an architecture and also from a project perspective. Yeah, thanks again. And for everybody, if you are interested in the next coming set of sessions, please go to Quant Q Summer School 2021.splashpad.com, and that's where we'll have information about future sessions, and we meet every Tuesday, and we hope to see you again soon. Thank you so much. Take care.